Welcome to 4.4 exponential and logarithmic function, doing some calculus on these guys. And I'll tell you the truth, this is actually one of my favorite sections. I find the exponential function exciting, and here's why. I really do. What we're going to do is take a look at this exponential function, y equals e to the x. Now, I've given you the graphs, and I've drawn the tangent lines on them. Now, why did I draw a tangent line on them? Because if I draw the tangent line at a point, what am I approximating? The slope of the tangent line. Okay, I can calculate the slope at a point. And what does that slope of the tangent line at the point give me? Like if I take a look at, it's the, I heard it, the value of the derivative at the point 1 right here. If I take this slope, I've got the derivative. Okay, so I've got this y equals e to the x drawn several times, and you got these, okay. What we're going to do, and I'll give you guys some time here, is, first of all, use your calculators. Well, the first one you should be able to do. Just, what is y equals e to the x? What's the function's value with e to the 0? You don't need a calculator for this. 1. And then you're going to plug it into your calculator because you got the button. What's y equals e to the 1? Well, you should know the approximate number after the next few months. 2.718 and then what? 28. Yeah. It's 2.718. I think I got a lot of decimals on here. 28. I'll go with 28. Okay. Then e to the 2. And then e to the 3. So, you guys know this, eh? If I just toss one down here that isn't on your list, and I left a space there, but I'll do this after, actually. So, you guys are going to evaluate e to the x, e to the 2. You guys just do that in the next second or two. And then we're going to talk about the slope at column. So what do you get for e to the 2? What do you get for e to the 3? Good. You guys are doing this. Okay. 7.38906. I'm rounding, yeah. Truncating is fine too, actually, on the AP exam. 20.0855. There you go. I'm going to cut it off. Now, the reason why I went to this many decimal places is because my slope calculations allow for that many decimal places as well. Now, the slope at x, y, at the point. So my x when it's 0 and the y is 1. When my x is 1 and it's 2.718 for the y. That's the slope. So I got to flip to these graphs. We'll do the first one. It's a pretty easy one to do. You don't even need a calculator here. So this first one here, let's take the furthest, it's the most accurate you can usually get is if you take the outer points, if you're actually using raw data. Now here, because I've got it pretty precise, pretty well accurately measured values, it doesn't matter. But if I take the slope of this tangent line, and it's tangent to the point 0, 1, we know how to do this, and you can do this slope in your head, right? What is the slope? So, you know what I mean. You're taking 3, 4, and -2, -1. You're doing the slope of that. I'm not standing up because my back hurts like a devil. And you're just applying the slope formula, right? Now, this, you don't have to write out your calculations, but just to remind you. So we're going 4 minus -1, y minus y, and 3 minus -2. And it is 1, right? Okay. So that's from the first graph that I gave you guys. Now, I'm going to just take this stuff over here, though. Just because it's too big for this. Eh? Now, I want to give you guys a moment. Do the slope for x for the 1, 2, and 3. So, flip to the page where I have at x equals 1 is the title, right? where I've drawn the tangent line. Do the slope from the outer 2 points. You could use the middle point, but if we're using scientifically collected data and stuff, you try to take it from the extremes are usually more accurate if you're doing a line, just because of measurement irregularities. This one, it doesn't matter. And then do it for 2 and do it for 3. I'll pause and you guys take a few moments to calculate the slopes and we'll compare answers.
Oh, the same number is.
Do you see what we're talking about? This seems alarming at first, and it's because it's a beautiful function. The slope of the tangent line is the exact same value as the height, the y value, at that point. Do you guys get what this means? Like, this is so bizarre, I think. At 1, 2.718, this slope of the tangent line is 2.718. Do you guys follow that? This is a weird, bizarre function in that sense, like that its own derivative. Now, typically you won't use a calculator to do these kind of things. Sometimes you will, but like, if I asked you to evaluate when x is 3 without a calculator, what would you just tell me this is? The best you could do is e to the 3, right? So you just say e to the 3. This is the same thing as 20.0855, right? And e to the 3. Okay, what is the slope then in terms of e? E to the 3, okay. Now, what if I said x equals, and I don't care, 50, something off, like my graphs, I'm going to 4, like, you know what I mean? It's off the map though by the time you get to 3, I think. Yeah, it is. So, even though I don't even have it, and you couldn't really take the slope, what if I put in here, I don't care, give me a bigger number. 760. Okay, what's the value that it's matched with? What's the slope of the tangent line there? 700. Okay. Now, this suggests that this is not a proof, but when the function is y equals e to the x, then the derivative is e to the x. So then the derivative is given, it's its own derivative. It's the same function value is the same as the slope of the tangent. What would be the, just think about this then too. What follows from this? What's the second derivative of y equals e to the x? Yeah, e to the x. If I ask for the fifth derivative, okay, it doesn't escape. That's the value of the slope of the tangent line. It seems bizarre because it just doesn't change, and you've been thinking of, when I do the derivative to x squared, it turns into 2x. When I do the derivative of that, it's just 2. You change things. This one, it's just a neat old function. So let's just think back then. We'll use this, and like I said, this isn't a proof, but it strongly suggests this, and you should never forget that. The exponential function, e to the x, is important because it's its own derivative. Now, to work with this, so I'm going to remind you of a few skills. You'll see that A and B are similar problems the way they're structured. I have a constant, 3 times something with an x in it. Here I have 3 times something with an x in it. That's why I'm doing A, then B. So I'm going to do A. Normally you just say, well, the derivative is 6x, right? But let's just talk about it like this. In this case, dy by dx is the constant, 3 times what? 2x. Right? And so, sure, it's 6x, but it's just the constant times the derivative, right? So, when you think like that, if this was just e to the x, the derivative would be e to the x. But when it's a function with a constant multiplied in front of it, what would the derivative in this case be? 3. E to the x. Yeah. 3 times e to the x. I'm going to just write it as 3 e to the x, and that's it. That's as good as it gets, right? Why minus 1? I know what you're saying. When we did this, subtract 1 off the exponent, that's where the x is the base. Here the x is in, it's a different structure like that. E to the x is its own derivative. There's nothing to do with subtracting or anything like that. Okay?
But you do inside outside.
Well, is this a composite function? Nope. So there's no insight. We're going to get to composite functions pretty soon. Before we do, let's look at what kind of rule would we use with this? Product rule. So, derivative of the first thing, leave the second thing alone, etc. So the derivative of the first thing, that's old school, yes.
So like it just says like e to the x, the derivative of e to the x. So if we have e to the 3x.
We're not doing e to the 3x yet, but that's a composite then. And we'll talk about that. Yeah. It'll be different. It'll be similar, but...
Because we had a question.
I know, but remember I said not to do anything with... Okay, anyways. Don't get to those until we've taken this section. I know what you're talking about. That was when Ms. Woolley was here, right? Remember how the day before that I said circle these ones, don't touch these ones? That was one of the ones you weren't supposed to do. Because you hadn't been taught this. Okay, 6x, right? To the 5. Leave this alone, leave the second thing alone. Plus, the first thing left alone. Derivative of the second thing is? Hey, we've actually done the derivative though. I don't want to say leave it alone, but it's its own derivative. Okay. Now, incidentally, with e to the x things, because of the repetitive nature of e to the x being used so often, you can usually factor some stuff out here. What are the two things we'll factor out on these? X to the 5. Somehow my board shut off. Is there? Okay. Now it's on. Okay. I was doing this last period too. X to the 5, e to the x is in common. And so left behind, the board is 6 plus x. Okay. How about d? Is there an x in this? This is a constant. This is some number, some decimal number. I keep throwing this back at you, right? If it's a constant, if I put cosine of pi times e to the 4, it's still 0, right? You don't have to. This is a constant. E to the negative 3 is a number, right? It's not e to the negative 3x. Okay? So, I just want to get that through to you. And then, this is where Rashad was asking. We're going to come up to the next page. And now you can do it. I know you weren't, Fiona had also shown me one of these problems that involved these and natural logs. But there was like, whoa. Yeah. But you guys were getting ahead of yourself. That's fine. It's not that difficult and you could do it, yeah. Okay, what about differentiating a function like your shot asked, e to the 6x? It's the chain rule. There's nothing new here, we're just applying that. In other words, take the derivative of the outside function, then the derivative of the inside function. Now, think of e to the whatever as the outside function, 6x as the inside function, okay? Now, so dy by dx. I'm going to just write this out as though this is e to the. Now I'm just really going to show the composition, okay? Now, I'm going to leave some space in front because it's typical that you actually put numbers in front, like 3x squared and stuff like that, not x squared times 3. It's still the same thing. So what's the derivative of the outer function? E to the. And in this case, don't touch the inside, right? So e to the 6x. times the derivative of the inside, 6 in this case. Now, like I said, I'm going to put the 6 here for a second, but I'm not going to leave it there, right? I'll put it here. I'm going to get rid of the dot. So, it's just typical that you'd put the number in front. If you do put it behind, put in brackets. Put it in brackets. So, do you see where this comes from? That's the chain rule. The inside derivative is 6. So, the chain rule with an exponential function. So I'm going to write it out like this. Y is equal to, we're going to say e to the u, whatever that might be. U could be 3x squared. Or no, I wouldn't do it that nasty. Well, you could. Actually, no, I would. Yeah, sorry. If it's that, then the derivative is equal to e to the u. You write it down as you thought, times the derivative of the inner function. So times, I'll call it u prime, okay? That's with respect to x. Du by dx, if you want to call it that. It's just more compact to use primes. Now, can I get you guys to try these ones here? They get progressively a little more complicated. Some involve the quotient rule by the very end. And we'll take these up in a flash. The first 3 you should be able to just do relatively quickly. You're learning something new, so it won't be super quick. Okay. First few, no problem there, I hope. By the way, when you have little expressions in the exponent, make sure it looks like it's raised. Don't make it the same size as your base e and so on. And I'm thinking probably, Zach, your penmanship skills, that's where you're going to have to be careful, okay? C, I noticed I didn't have the y equals. I think you guys understood that to be implied, though. But the derivative of that, before I do that, why not make it easier to think about? Don't use the quotient rule if I haven't stipulated you must do it as printed, right? Which I do on tests sometimes because I want to see if you can use the quotient rule. Anyways, so that makes it a lot simpler, right? Flip it up, negative exponent, and then you got negative 10 e to the negative 2x. Okay. The next thing, this one, use the quotient rule. Let's see. Well, or is there a better way to do it if you don't want to use the quotient rule? Okay, we can flip it up. Is that what you guys did? I heard it 50-50. Okay. I'll do it both ways. Okay. If I use the quotient rule, I'll do that one in red. It's equal to the derivative of the top, leave the bottom alone. Now the derivative of the top is e to the x squared. What's the derivative of the x squared part? 2x, so I'm going to put that down. 2x times the bottom left alone. Plus, minus. And then the top expression left as is times the derivative of the bottom over x to the 6. Now, if you were to simplify that,
You can take out EX squared and X cubed.
you could definitely take out x squared, not x cubed on the top. So, think this through. I'm going to take out x squared, yep, squared, e to the x squared there. Now, what's left behind? I'm running into my top shelf there. So what's left behind here? Okay, if I divide this out by x squared, do you notice that I get rid of this, but it's still x to the 1 here? And this, 2x, so 2x squared. Okay? Yep, right. 2x squared minus, I've taken the e out, so just 3. What happens to this x squared next to the 6 here? I'm going to just erase it because I'm out of space. I'm going to call that x to the 4. I'm just moving this over so I can erase it a little bit. And then I'm going to take that out, and that becomes x to the 4. Okay. I'm only doing that because I ran out of space and I want to fit the other one. right? X to the 4. Okay, sounds good, right?
What happened to 2x?
X squared?
Divided it.
I had X,
Oh, you took out x squared and then you divided it. Oh, okay.
and this was X to the 6. To cancel it out, it simplifies to X to the 4. Okay. Now, the other way of trying it was, what if you rewrote this? X squared in the exponent spot times X to the negative 3. Now, we know it's the same answer, right? Did you guys get the same answer? No, but somebody who did. Is it an equivalent answer? You might have X to the negative 4 in front if you factored it. You should. It's the same thing. It's the product rule then. I'll leave it be then. Yeah?
Could I double the exponent? Because it's like e to the x to the 2.
With the square in it, yeah?
So how'd you get the 2x in front? Did you just do the derivative of the top? And then
Yeah. The derivative of e to the x squared in the exponent position is, first, the derivative of the exponential function is just e to the. Don't touch the inside. Then do the derivative of the inside, which is 2x.
Is that why it says x squared still? EX?
Yes, because you don't touch anything inside the composite function for the first thing, okay? And then if you wish to do it with the product rule, you'll get an expression. It'll involve x to the negative 4, though. But x to the negative 4, you can see how that winds up being the same thing. These questions are relatively quick and easy to do. You now see how that's related to the questions you had on the multiple choice ones that some of you will probably befuddled with last week. Don't touch, now you can. Don't do anything with a natural log in it yet, though. Then, though, what I want you to do before that, though, is to make sure for tomorrow, page 1 and 4 of the assignment. Maybe try those right away, okay? Get some practice. Don't try the assignment marked ones for the E's until you've got a little more practice with this, okay? So I do want to be able to get a head start on marking page 1 and 4, though, ahead of time, okay? So maybe do those first, then come back to this assignment. I've got to stop this.